In this video, we're going to briefly talk about what open channel flow is, and we're going to move on to how we get to the Chezy and Manning equations and what they are. But first, we should obviously understand what open channel flow is. And open channel flow is any kind of flow that involves the flow of a liquid in a channel or a conduit which is not completely filled. When a channel or a conduit is completely filled, that is termed as pipe flow. When it's not completely filled, we're talking about open channel flow. So what that means is that if you've got, hold on, let me just draw it here. So let's say you've got a surface, and on top of the surface you've got fluid flowing on top of it. Okay, so if this conduit is not completely filled, then that means you've got a free surface that exists between the fluid that is flowing. So if, let's say, this is the fluid that is flowing in here and you've got water, then there's going to be some other kind of fluid that is going to be flowing on top of it, and that is usually the atmosphere. So that's usually air. So you've got a free surface that exists between the flowing fluid and the fluid above it. And other than that, the main driving force of these kind of flows is the weight of the fluid itself. That means that the fluid is flowing because of gravity downhill. Examples like, for example, just river flow, water flowing in the river. That is a very basic example of an open channel flow. And because of the existence of this free surface, now you can have various shapes on top of it. Okay, that means that the fluid that's going to be flowing on top of it, because of the air, uh, it's going to distort the shape of the fluid, so it's not going to remain, strictly speaking, it's not going to remain like this. There's going to be waves that are going to be taking place. So that's why you've got surface waves, then maybe of different kinds of forms, and that is what you see when you go to the beaches or something like that. So you've got surface waves that exist. So that means that you need to look at the basic properties and characteristics of surface waves as well. And for example, when we talked about pipe flow, there were different ways that we were classifying pipe flow. So we had something like a developing flow, and then we had a fully developed flow. We had the entrance region flow, we had the fully developed flow, we had laminar flow, we had turbulent flow, and so on and so forth. So just like that, we need to identify and classify different types of flows for an open channel flow as well. And because of this free surface here, that means then the fluid can basically select different configurations now, and it can be different types of flow now because it's not completely filled up in a pipe or a conduit. So then the manner in which you will basically select what kind of configuration it is depends on not just the depth of the fluid, okay, in y direction, not just the depth of the fluid, which is, let's call it y. So it's going to be, the fluid depth could vary with y, so with time, or it could also vary with distance as well. Okay, so that's one way to classify open channel flow. Let me just repeat that. That the fluid depth here, y, this can vary in terms of time, of course. So if you've got, let's say, this surface here is not a fixed surface, and this surface can move, so then that means that with time, it's possible that the surface eradicates and you've got more fluid depth now over here. Okay, so then that's fluid depth y varying with time. It's also possible that as the distance is increasing, maybe the fluid depth now starts increasing or decreasing more. So then now the fluid depth is varying across the distance in the channel, which is x. Okay. So if the flow depth at a given location is changing with respect to time, or if it's not changing with respect to time, then that's classified as unsteady or steady flow. Okay, so if it's not changing with time, then that's a steady flow. And if it's changing with time, if the surface is eridicating or some other reason maybe, then the flow is going to be unsteady. We're only looking at steady open channel flows. Okay, and then these open channel flows can be classified further. So, if, for example, you've got open channel flows which are classified as uniform flows. Okay, and when we say uniform flows, what we mean is that the depth of the flow here does not vary along the channel, along the distance of the channel. So the depth of the flow y is not going to be varying along the distance. So dy by dx along the distance x of the flow. So that means that dy by dx change is going to be 0. Okay, because the depth of the flow is constant. Then we've got non-uniform flow types or varied flows. And then what that means is that the depth is varying across the distance. So dy by dx is not going to be 0 in those cases. Okay, that's called a varied flow or varying flow. And then this varied flow can be classified into further 2 types. You've got the rapidly varying flow, which means that the flow depth is changing considerably over time. Okay, like let's say like a spillway. Okay, so then when we're looking at a spillway, the depth of the flow changes rapidly. So that's rapidly varying flow. And then you've got gradually varying flows. Okay, you've got gradually varying flows, and these are the flows in which the flow depth changes slowly along the distance. So in these cases, for gradually varying flows, dy by dx is going to be very, very small. And it's going to be a lot smaller than 1. Okay. And when we're talking about the um, rapidly varying flows, then over there, dy by dx is approximately or close to 1. Okay. So these are the 3 different ways how you can classify an open channel flow based on the depth of the flow. Now you can also classify this flow geometry for an open channel flow on the basis of whether the flow is laminar, the flow is transitional, or whether it's turbulent. So then that means you need to look at the Reynolds number. Okay, so when you look at the Reynolds number for an open channel flow, then you write it in terms of rho v r h. So you go with characteristic length or characteristic diameter, or RH here represents the hydraulic radius. I'm going to talk about it in a second. And then you've got mu viscosity. Okay. So if the Reynolds number is less than 500 for an open channel flow, then you've got laminar flow. And if the Reynolds number is greater than 12,500, then you've got turbulent open channel flow. And if it's anywhere in between the two, then you've got transitional flow. Okay. And RH over here represents the hydraulic radius, and the way that you evaluate RH is in terms of area divided by perimeter. Okay, so you've got the area of the section over which the fluid is flowing, and you've got it's the ratio of area of the section divided by the perimeter, and this perimeter is called the wetted perimeter. And what that means is that it's the length of the perimeter of the cross section that is only in contact with the fluid. Okay, so that's called the wetted perimeter. So what that means is that if you've got, let's say, a fluid, let's say you've got a fluid flowing on top of this, and then you've got your free surface here. Okay, then the wetted perimeter is going to be just this one, the one that is in contact with the fluid in here. Okay, the wetted perimeter is going to be all of this, and we exclude this side because the interaction between the fluid here and the atmosphere is assumed that it's negligible. So we don't include this portion of the perimeter in the definition of the wetted perimeter. So that's how you evaluate the hydraulic radius to calculate the Reynolds number. And what you will see is that most open channel flows that involve water, at least, um, are turbulent flows. Okay, so for example, if you're looking at flow of a water in a river, um, and let's say the water is at 10 degrees, so across that 10 degrees you can calculate the viscosity, V, and let's say that's around 10 to the power minus 5. Okay, so let's say 0.1 and 10 to the power minus 5 meters square per second. And let's say that you've got an average velocity of 0.3 meters per second. Okay, so what that would mean is that if you have, let's say, a hydraulic radius given to you as well, or you could calculate it yourself, but if you have, let's say, a hydraulic radius given to you, which is 3 meters, then from here you can calculate the Reynolds number for this open channel flow, and that's going to come out to be somewhere around 7 into 10 to the power 5. Okay, so that means that you've got a turbulent open channel flow. Okay, this is represented by RE, and this is your Reynolds number. Okay, so that's how you work out Reynolds number for an open channel flow. Besides this, like I said, because of the existence of the free surface between the fluid and the atmosphere, then that means that the character of the open channel flow could also strongly depend on how fast the fluid is flowing relative to a typical wave that is moving relative to a fluid. Okay, so then what that means is that you need to go to a dimensionless number that gives you that kind of ratio, and that is fluid number. And fluid number is basically a ratio of fluid speed to wave speed in the first place, so you can use fluid number in terms of velocity of the fluid divided by wave speed, which is into 1 by 2 to the power 1 by 2. Okay, and the length here is the characteristic length of the flow. So based on this fluid number as well, you could go ahead and take a ratio of the fluid speed to the wave speed. Also, another variable that is then important is that what could be, let's say, the slope of the bottom channel. Okay, so that is usually represented by S naught. Okay, and it could be different for different kinds of flow and different kinds of situations, but usually slope of this is called the slope of the bottom, S naught. So the slope of the bottom usually for open channel flows is very, very small because it's nearly horizontal. So for example, when we're looking at different kinds of rivers, we can find in the literature what the S naught value would be for them. And usually for a river, the S naught value is somewhere around 0.0001. Okay. So the S naught value, the slope of the bottom is usually small enough, but we still need to take care of that and include it in the list of variables that are important when we are trying to work out any kind of flow, but especially, for example, when we're looking at the uniform flow. So for the uniform flow, what we have seen is that you've got S naught, which is depth of the bottom, that is important. You've got the size and the shape of the channel cross section that is important. So you've got area that is important. You've got the hydraulic radius that is important in terms of the bedded perimeter. Other than that, you also need to know what kind of material is your channel made of. Okay, so if it's obviously if it's gonna be let's say um, a natural channel, so for example rivers, then the character of this channel is going to be different. If you're looking at, let's say, artificial channels, then you're looking at maybe glass, you're looking at steel, you're looking at cast iron, then the character of this channel is going to be different. So then you need to look at what that character is, and usually the character of the material is given in terms of N, which is a coefficient that is usually available in the literature in the form of tables, and it's called the Manning coefficient. Okay, so the value of N is something that you need to see from the literature. And then what else could be important? The velocity of the flow could be important, the average velocity of the flow, and then based on the average velocity, you could also calculate the flow rate, which is Q. Okay, so these are different parameters that are involved in studying open channel flow, especially when we're talking about the uniform depth open channel flow. Okay, and I'm not going to go into a lot of detail with it, but I just wanted to show you why these terms are important for a uniform depth open channel flow, because on the basis of these then we go ahead and see, so for example this is the uniform depth open channel flow. So for this, what we see is that we have an age-old equation, probably one of the oldest equations in fluid mechanics, and it's called the Chezy equation, which is given in terms of the hydraulic radius and the slope of the bottom of the channel. And then you've got C here, which is a constant, and this is usually termed as the Chezy constant, for which the values are usually calculated on the basis of experiments. It's not dimensionless, and Chezy was basically a French engineer. He designed a canal for the Paris water supply. So this equation is from back in 1700s. Okay, so from this Chezy equation, then Manning, who was another engineer back in 1800s, he developed a more modified equation on the basis of this to more accurately then describe velocity in terms of the hydraulic radius, the slope of the bottom, and this variable n, or constant n, which takes into account the surface material of the channel as well, because that is something that is not being accounted for here. You have to calculate it experimentally for different situations. So instead of that, Manning made it more accurate, this expression more accurate in terms of these. And the value for n then you can find out from different tables. So for example, this table is from Munson's book, and you can find out for different types of bedded perimeters, you can find out the value of n. And then if you know the velocity, then you can find out the flow rate by multiplying the velocity into the area. Okay, and then that is going to be of this form. So Manning equation is used to obtain the velocity or the flow rate in an open channel flow. Chezy equation was the basis for that. Another important thing is that, for example, when we look at the value of n or the value of c, these are not dimensionless numbers. They have dimensions. Usually what we've seen is, especially for pipe flow, we move towards the dimensionless form of the equation. So the coefficients then that appear in those are also dimensionless coefficients, like friction factor in pipe flow, or like drag coefficient that we saw for flow over immersed bodies. But because these two equations, the Chezy and Manning equations, are so old and they've been used for such a long time and they're widely recognized, then that means that we've gone away from the dimensionless forms, and uh, for this specific scenario, we are using equations that are not dimensionless. So we need to go and look at uh, what the units for n are, what the units for c are, and these equations are valid, these two, only when we are looking at SI units. If you were to change it into the British unit systems, then you would have to multiply it by some number in order for you to get the right value. Okay, so these equations are valid only in SI units. Okay, so this is just an introduction to the open channel flow, and you can go ahead, and if you want to take a look at more detailed information about this, you can go to Munson's book, chapter number 10, and take a look at section 10-4 for uniform depth channel flow.